I'm Steve Wang. I'm a statistician at Swarthmore College, a small college outside of Philadelphia. Several collaborators and a large number of students have worked on this project with me, and they're shown here. My research focuses on statistical paleontology, but a couple of things drew me to North Atlantic right whales. One is that I've long been interested in whales just as a layman. They seem like such cool and magnificent creatures. The second is that some of the issues seemed analogous to the issues I deal with in paleontology, so I saw an opportunity to use those methods here. Feel free to share any of this on social media. What we're trying to do is to estimate the population size of the North Atlantic right whale, how many individuals are left. We're going to use the right whale catalog, but of course you can't just count up the number of individuals in the catalog and use that as the population size for two reasons. One is that some of the whales that were previously cited are now dead, so we have additional whales in the catalog that are no longer alive. The second is that some whales that are now alive have never been cited and are missing from the catalog. Turns out we can deal with both of these problems using statistical methods from paleontology. The first problem, that there are some previously cited whales are now dead, what we're going to do is to estimate the probability that an individual is now alive based on its sighting record. If a whale was seen regularly but has not been seen in a long time, then we probably estimate that there's a high probability that's now dead. On the other hand, if a whale has been seen recently, it has a high probability of being alive. Estimating these kinds of probabilities is what I study in paleontology. I'm trying to estimate when a species in the fossil record went extinct. And this is an analogous problem for whales, except for we're looking at when an individual became dead as opposed to when a species became extinct. The second problem about some whales that are missing, there's a long history of work in statistical ecology on estimating the number of unseen species in a population. Here, the problem is analogous, except for we're looking at unseen individuals rather than species. The idea is that if you look for individuals and you continue to see new individuals every time you look, so you see different individuals, then there's no reason to think you've seen all the individuals, because the next time you look, you might very well see another new one, and therefore there are more out there to find. On the other hand, if you keep seeing the same individuals over and over again, then it suggests that you've seen most of the population and there aren't a lot of unseen individuals. So I worked on a project similar to this, but looking at dinosaurs, trying to estimate how many kinds of dinosaurs, genera of dinosaurs, had not been found yet. And so what we did is to use this kind of idea and look at the number of fossils found per genus of dinosaur. So how many genera were known from one fossil, two fossils, three fossils, and so on. And if you make a graph like I'm showing here, what you really want to know is the bar that's zero. How many dinosaurs are known from zero specimens? And that is the number of unseen species. So we're trying to estimate what that bar is. And that's a challenging problem, but there are ways to do that in statistics. So we're looking at an analogous problem with whales, but trying to estimate unseen individuals rather than species. So what we do to put all this together is for each whale in the catalog, we take its sighting record and estimate the probability of it being alive. We also have additional information, such as whether it was sighted entangled or with a vessel strike injury or other information. And we use those variables as covariates in a logistic regression and use that to adjust the probability of being alive upward or downward. And so now that we have all those probabilities, we basically flip a coin, run a simulation where we're flipping a coin for each whale. So we're going to flip alive or dead, and the probability of being alive will be that adjusted probability that we've estimated. So you can see in this table, the first whale has a 96% chance of coming out alive in the coin flip. The second whale has a 63% chance of flipping alive, and so on. So once we do all the coin flips, we take out the whales that are flipped to be dead in the simulation and take just the alive ones. And then we send that information, their sighting records, to the method for estimating the number of unseen whales. Then we run the simulation all over again, flip coins again. We'll get a slightly different number of whales that are alive or dead and use the alive ones and send that to the method for estimating the number of unseen whales. We repeat the simulation a large number of times, perhaps 1,000 times. Each time we get a slightly different set of living and dead whales. We get a slightly different number of estimate of unseen whales. And putting all that together with the known whales, we can get a posterior distribution for the number of total whales. And so this is what our posterior looks like. This is still somewhat preliminary results, but you can see it's fairly similar to what the PACE model, the 2017 model, is getting, even though their model works in a completely different way. So I think that gives us some confidence that the methods that we in PACE are finding are in some sense correct, and there aren't a lot of additional whales out there. Okay, so thank you for listening, and I'd especially like to thank Amy Knowlton, Heather Pettis, and Philip Hamilton for patiently answering all my questions as a non-whale specialist over the years we've been working on this.